name is Johannes Leppä. I work as a data engineer at Komodo Health in the data ingestion team. And I'm going to talk to you about our data ingestion architecture. And in this talk, first, I'll say a few words, just a few words, about Komodo Health as a company. And then I dive into some of the data ingestion challenges that we have at Komodo, and then explain the architecture that we have to tackle these challenges. And after that, I'll discuss a little bit about the things that we've learned while doing this journey to get into that architecture, and then afterwards, and also some future developments that we are working on at the moment. And in the end, I will also talk about the ingestion process itself and how to scale that on top of the architecture. So Komodo Health is a private company founded in 2014, and our mission is to reduce the global burden of disease through a most actionable healthcare map. So what exactly does that mean? We have data of all the different aspects of the entire healthcare system. That could be health insurance companies, doctors, hospitals, clinical trials, scientific publications. So there's a lot of aspects in this, and we're bringing all of that data together and have an AI platform built on top of that to draw insights to our customers. And to give a simple example what sort of value this provides to our customers, let's say that they have a project coming up for a clinical trial or something like that, and they need to figure out how to best allocate their resources, how much do they need, and what's the best usage of the resources that they could have. These are kind of questions that can be answered with the data that we have. However, there are several challenges in that for the data ingestion, and one of the things is that since we want to be very comprehensive, that means that we need to have all the data. And that means there's a lot of data sources, and there's also a lot of variation in these data sources. Some are public, some are proprietary, and the sizes of the data, there's a huge variation. They can be just megabytes at times, or go into multiple terabytes. Usually not really huge amounts of data, but there is a big variation still to handle. And also the refresh rates, it's not streaming data by any means, but we may have daily refreshes for certain data sources, while others might be refreshed only on an annual basis. And what you would build to handle these works would be very different depending on these parameters. And when we are integrating new data sources, what we often have is a historical drop in the beginning that might be much larger, and after that we have incremental additions on top of that. The first thing in our ETL process is obviously get this original data extracted to our system, and there we come to the next challenge, which is the interfaces that we need to deal with. This data could be on SFTP or FTP servers, different cloud providers, could be AWS S3 or Google Cloud. We might use APIs to get the data or download it from internet. We even get data delivered us on hard drives. So we need to figure out how to interface with all of these. And once we have these original files transferred to our system as they are, we do a minimal amount of transformations just to convert these to a Parquet format that we can then use later on. And there, a big issue is that, again, these various data formats that we need to deal with. We have a lot of CSV files. Also, we need to parse XML files, and we have more rarely SAS data files, fixed with files, and all of these different file formats have their own nuances that we need to somehow handle with. So it's very difficult to provide something generalized to handle all of the data because of these differences. We also get data in Parquet format, which might seem very nice because Parquet is what we are putting it into, but there it's actually tricky because of the row groups and that we were getting were so small that the I/O just reading those files was very terrible. And also these files could be compressed in different kinds of formats, or the data could be encrypted. And then under the data ingestion, we also have some pre-processing steps before we provide it to our internal users. And especially in cases where we have several data sets that cover a similar aspect of the data, then we need to define a common schema and then map all these data sources into that common schema in a step we call commonization, so that we can actually make some sense of the nuances and differences in those data. And whatever we do, there's obviously security and privacy considerations. I mean, obviously, everybody wants to keep their data private and not let anybody else to get access to it. But when dealing with healthcare data, there are additional requirements and compliances that we need to deal with. So before we had a centralized system, we were still ingesting the data, but there is always the question of priority. And these are our data engineering values of scalability, maintainability, robustness, and reliability. I'm sure everybody in the audience agrees that these are great things to go for. But also, there's the rapid development, which in a small company is often requested. And it's not really that you choose one or the other, but you have to balance these two things, like what is reliable enough and when you need to move forward faster. So often, in our case, we have to emphasize moving forward fast and provide value to our customers. But the good thing in that is that you become agile to changing requirements. So if you spend a lot of time working on something that is perfectly engineered, but once it's done, it's already obsolete because you need to do something else, you have wasted all that effort. So moving forward and building on top of it is a better choice. But this has some consequences. These are very on a high level, but they apply to data ingestion as well. So we have very specialized pipelines often, because especially in a case when we did not have a data ingestion team as a team yet. So it would be different developers doing data ingestion more or less ad hoc basis. So they build something for what they need to get done and not something generalized. And if there are manual operations that you only need to do, let's say every month, it might be faster to just do it manually as opposed to automate that process. And then when it's different people working on these tools, they have different ways of doing it and in general, less reusable code. So why did we build a centralized ingestion system? Those issues that I mentioned, in the end, it was becoming difficult to maintain the previous approach because onboarding engineers to the processes was tricky, and also the manual steps were accumulating and taking more time to operate. And then finally, what pushed us over the cliff was that we had a project to integrate a few new data sources. And all of these would have had daily operations on them, and we really did not want to do those manually. We wanted to automate them. And also, these sources were pretty similar to each other, so it wasn't too difficult to build something that was at least general enough to handle these sources. And if we do it correctly, we can also migrate other data sources to the same system afterwards. And why building as opposed to buying? We wanted to be flexible and leverage the experience that we already had with the tools. And this was actually something that had a big impact on the technologies that we chose, because we were already using several of these technologies, and we were looking at them and thinking that these actually fit to what we need to accomplish. It is not a bad compromise to use them. These are tools that are suitable for it, and we already have this this knowledge of how to use them. So it's a low-hanging fruit to use them for this purpose, and this provides us flexibility to also reuse whatever we had already built using these tools, what codes we would have. So finally, getting to the architecture itself, what did we actually build? So on a high level, we're using Airflow to organize the workflows and schedule them, and also provide alerting. That's obviously something you need if you're automating workloads. You want to get alerts if something goes wrong so that you can react to that. And we are using Spark to distribute the processing. And both the Spark and Airflow components are running in containers managed by Kubernetes, and the infrastructure is running on AWS. We're using EC2 instances as the machines, and then saving data to S3. Airflow is actually a very central component in the system. We have a lot of good functionality out of it. We really like the fact that we can organize the workflows into DAG using Python code. We had Python coders in the team. Most of the team was coding in Python, and we want to have it in a code. We were earlier using some tools that would have more UI-based approaches, and we really would rather have things in code. And also, Airflow provides hooks that are useful for this issue that we have of having several different kinds of sources we need to interface. So now these hooks, SFTP hook, S3 hook, and so on, allows us an easier interface with these sources. And another good thing to simplify our process was the operators. And for example, in this example tag that I'm showing here, we are using SFTP to S3 operator to do the data transfer from external SFTP to our S3. And this is something that repeats over and over again in our data pipelines. So now that we have this operator, we just configure that operator, and it will accomplish the same task in several tags. Then Airflow provides alerting on success and failure of the task straight out of the box. That was very useful for us, and also high-level monitoring. So we see the statuses of the tags, if they are running, if there are failures, if there are successes. So at least certain level of monitoring is provided immediately. And with Airflow, we can parallelize the execution of the tags and tasks. Some of the negative sides, though, as useful as these hooks and operators are for us, they did not really work out of the box for us. We had to figure out how to customize them to our purposes, especially in terms of passing credentials to access different resources, for example, encryption keys on S3 and that sort of things. So we had to work on those before we could actually get them working as we wanted to. Then Spark, we use that for the transformation and pre-processing steps in our pipeline. And Spark is already a pretty mature tool, so we found it to be very reliable what we are doing, because our processing is really bread and butter work for Spark. The data amounts are not super huge, and we are not doing anything crazy here. We are joining tables, filtering data, doing some small changes. So this is something that is extremely simple for Spark to handle. And also, it provides Python and Scala API, because we have both Python and Scala coders in the team, so that is also been very useful for us. Perhaps the one issue that we've had is the performance tuning. It is much easier to write code that does functionally what you want to do than then actually do it in a performant manner, and finding that information is a little bit trickier as well. And so that's the part where it could be easier to do. And then here, we see the different layers of this infrastructure, and this is actually a very important part of the architecture, is the interaction between these layers. So at the bottom, we have the AWS layer, where we have the EC2 instances, which are then registered as nodes with the Kubernetes master to provide the resources to the Kubernetes cluster. And on the other hand, there's Spark Master Airflow components like Scheduler and WebUI that are running in containers in pods. That's a Kubernetes context for environment to run these containers. And these pods are then landing on these nodes to execute them. And besides managing all of this, Kubernetes provides us very nice features. For example, the isolation of environments into namespaces. We can have one cluster having both dev and test environment running, and they are in their own silos in the namespaces, but still use the same cluster. That's very convenient. And on top of that, we use node selectors to allocate resources. So the instances that we have are connected to autoscaling groups on AWS, ASGs, and all the instances related to an ASG, when they are registered as a node, they have a label on them. And we use those labels to guide the pods to land on these specific nodes. And this allows us to scale these resources for specific use cases. So if I'm scaling my ASG up and get those nodes, I know that only my pods are landing on those, so I get those resources for myself, and no one else is going to take those. And this is useful when you have several users in the same cluster. The issues with Kubernetes, though, occasionally we've had some stability issues, especially networking issues, where we have not been able to connect to the cluster properly, or DNS resolution inside the cluster has been problematic. And these are something that are pretty serious considerations when they happen, because it has a big impact on our operations. And when these have happened, we've found them also a little bit difficult to troubleshoot. Finding the information, what exactly is going wrong, is not very straightforward. So this is now a list of things. If I cherry pick all the positive things of the past slides that I get a list of very nice things. I could say that, yes, we got this perfect system, we crushed it. If I was a salesman, I would leave it right here. Lucky for you, I'm more honest than that. So the devil is in the detail. So let's look a little bit on what sort of issues we have had and limitations with this architecture, what we have learned while working on this. This is one of the limitations. We have, in our workflows, we have big spikes in what we need to process. And there is the problem that even if we could scale up the cluster and it could handle these workloads, but if we would keep it scaled up that much, that would be extremely wasteful because we would only need all those resources for a short amount of time. Most of the time, much less resources would be enough. We can scale it manually, and it's not too awkward. We will scale up the auto-scaling group to get the nodes, and then scale the replication controller to get the pods. But in that situation, it is still a manual task to do, and the problems come when we are trying to scale down, because the information on these different layers is not passed perfectly. So for example, if we have Spark workers, and most of them are not doing anything, but there are executors running on some of them. If we now scale down the replication controller for the pods, so that we are terminating some of them, Kubernetes layer does not know which one of those workers are actually having executors running on them. So we could lose the ones that we actually would like to keep on running. So as a result, we are currently running the big workloads on separate clusters. We have scripts to bring up a cluster for that specific purpose. We run the big workload and take it down. Those big workloads doesn't happen too often, so it is not too awkward to do, but it is still a manual operations that we are not happy with. Another issue to stay aware of when we have been doing this scaling up and down and seeing how things go, we noticed that we might end up in a situation where 2 Spark worker pods were landing on a same node. And the reason of existence for a Spark worker is to have resources to report to the master. That's what it does. So in our case, both of these Spark workers see all the resources on that machine and report it to the master. So now the master thinks that it has twice as much resources than what it actually does. So we obviously don't want that to be happening. And Kubernetes does provide pod anti-affinities that can be used to prevent this from happening so that 2 workers will not land on the same node. And then the exciting part, how are we going to solve this problem? What are we going to do in the future? And this is what we are currently moving towards, is using Spark directly on Kubernetes. We get rid of the master and the workers altogether. We will just have the Spark applications talk directly to the Kubernetes master. Hey, these are the executors that I need. And then these executors are running on containers and have their own pods. And another good thing with this approach is that now when these executors are created, if there are not enough resources for those pods to land on the nodes, we can use Kubernetes Autoscaler to recognize that and now scale up the ASG to get those nodes and for the executors to land. And after they are finished with their job, they will be terminated, and the autoscaler will again recognize this and will scale down those machines as well from taking resources. Another problem that we have, or limitation in the system, is with the Airflow scheduler. We are running the scheduler using local executor, which means that all the tasks that are being executed are executed as sub-process of the scheduler. So now, if we have parallel tasks, we could have several Spark applications and some file transfer going on. All of these are executed in that same container, on that same node, using the same resources, in which case, in order to scale that, we just need to get a bigger machine to run that scheduler on. So that's not a very good way to scale those resources. But the even bigger issue is that it becomes a single point of failure. If the scheduler goes down, something happens to that pod, all the tasks that we're running will fail. And in general, we have the self-healing in place. So now when the Because of the replication controller we have on Kubernetes, when the pod goes down, the scheduler pod goes down, a new one is created, and so the scheduler comes back up. And if the tasks failed properly, they have marked it to the Airflow database as a failure, and they can be retried. So we can just continue business as usual. And in most times it works, but there are issues with the self-healing. And one of them is the possible inconsistencies in the Airflow database. If the scheduler died ungracefully, those tasks might not have updated their status to the database. They might still seem there as a running state, even though they are not running. And obviously, then they are not retried and will not be able to finish. And also, if these tasks were depending on a local file, now that the pod is gone or even the instance have rebooted, you might lost the file that you were depending on. And in this case, again, the task will always be failing. And then finally, for a long-running service such as the scheduler, there could be logs, temporary files that are accumulating on the disk. And after some point, you run out of disk. And due to disk pressure, your pod gets evicted from the node. And now, in our setup, where we are using the node selector to guide the new pod always to land on that same node, in this case, it becomes the problem that that pod would always get evicted because the disk is still full. And this would cause an outage in our system. So having said all of these problems with the local executors, a reasonable question would be, why on earth are you still using it? And the answer pretty much is because we can. So that's the most simple solution to start with. In the beginning, we had just a couple of data sources. Local executor was perfectly fine to handle them. We had absolutely no issues there. So we only wanted to build more complexities to handle in a more distributed manner once we need to do that. And to be honest, I've been a little bit surprised how long we have been able to get away using just a local executor. But yes, again, the exciting part is that we are moving away from it to use the Kubernetes executor, in which case these tasks are now executed on a separate pods and to isolate these processes. And again, we can use the Kubernetes autoscaler to scale the resources to do that. But finally, I would like to go a little bit beyond the infrastructure and think about our data ingestion process in general. So if we think about what our data ingestion team needs to accomplish, what is our priority? We are not really in a business of building data ingestion solutions. That is just a tool for us that we need in order to meet these other priorities, which are to deliver the data to our users fast, and obviously deliver good quality data to them, and to do that in a way that is within our security and privacy compliances. And to do that, the bottleneck rarely is the infrastructure. We don't really spend that much time working on this infra and improving that. We spend most of the time actually integrating new data sources that are then run on top of this infrastructure. So here are some things that we have done in order to scale those processes as well. This is, again, a diagram of our ETL process, this time showing for these data sources that we need to commonize to bring them into common schema to make sense of them. And there becomes the issue that when we are integrating a new data source in the beginning, we don't really know how we need to do that mapping. We need to figure out what are the columns in the raw data that we need to map to our common schema. And there, to help with that process, we have a data profiling tool which automatically tries to recognize these columns based on the previous data that we have, and also some regex patterns and that sort of things. So these suggestions that it provides helps us with the commonization step. And once we have recognized some of these columns, we also run a data validation on them to see if the data looks good or if there are any issues. And if we recognize any issues, then we can communicate it with the data source to see, like, hey, what's going on with this data? Like, why does it look like that? Do you have some issue, and what's going on? And obviously, this is something when we are communicating with external parties, we want to have that iteration to happen as fast as possible. If it takes a long time before we notice this, then we cannot deliver the data as fast as we would like to. And another thing that we do in this step is to look at the assess a little bit some of the compliance-related risks. For example, if we notice that there are open text fields in the data, those are much more likely to contain private information compared to structured fields, for example. Then the next step is the commonization itself. And it's kind of annoying. It's very similar to these data sources, but we still cannot properly automate that, because all of these sources have their own unique features. We always have to figure out what to do with them on a case-by-case basis. And so, but what we have been able to do is to build a tool that does the commonization based on a configuration file. So that this configuration file is just a JSON blob that describes that, hey, these columns in the raw data map these in the common schema, and then these are the tables that you need to join, and this is how you join them, and so on. It gives that description, and then the code is able to figure out. There are not too many edge cases that we need to handle because of the similarity, so now we can have generalized code that can actually handle the commonization part with that configuration file. And the good part in that is that we don't need to make new code for that. So then this configuration file could be done by someone who just understands the data but doesn't have to be a technical person. So you don't necessarily need an engineer to do that. And then finally, if we have issues, if we have bad quality code or our infra is failing, yes, engineers need to work a little bit more to get those fixed. But outside of that, if we are delivering good quality data, like the stakeholders will not care too much about these technical nuances. So at the end, we do data validation to make sure that what we are producing out is what we would expect. So we have created data standards that for this particular type of data source, this is what we expect. And when we integrate a new data source, we will then see if these data sources match to that standard. And if they do not, then we will either notice that there might be something wrong in our commonization step. Maybe we had a bug there and we need to fix that. Or maybe it is an issue with the underlying data, in which case we again go back to the source to say that to communicate what's going on there. And if we, in those cases, we also see if we can improve the data profiling tool to handle in earlier stages these sort of issues in the future. And obviously, what sort of, these are the tools that have helped us to scale these processes, that we would spend less time on these new data sources that we are integrating. And obviously, it depends on your own use case, like what your process would look like, what sort of scaling you would need on those processes. But this is still something that you should consider when you're thinking about your data ingestion as a whole, not just the infrastructure. Though on the other hand, the infrastructure should be flexible, that you can also create these sort of tools that you need to help in these processes. For example, these are all running on Spark as well, and running on Kubernetes. So we are using the same infrastructure to run these tools as well. So to conclude, we have found that this architecture with Airflow, Spark, and Kubernetes is very flexible for complex data ingestion. It has served us very well. But there's no free lunch. There's a lot of nuances with these tools. We spend a lot of time learning how these tools work and also how they interact with each other. So there is a learning curve to get things running smoothly with them. But the good part is that these technologies are constantly improving. For example, some of these future developments that we are now working on that I mentioned, these were not available at the time when we started to build this system. They were only introduced at later stages. And then, reminder that it's not just the infrastructure that needs to scale, it's also the processes that you need to do. And you should look at the whole picture when you're thinking what your data ingestion needs to accomplish, to make sure that you know what are your priorities and how you are meeting them. And with that, I would like to thank you for your attention.
So for your data profiling and data validation, is it just some data quality operator to do the quality check or not?
Yeah, so a bit more details on this. On the data validation, it's pretty straightforward because there we have more or less exactly, we know what the data should look like. So there we can have regex patterns or even some like value lists that these are acceptable values. There is a limited number of states in the United States. Like you can just use a list to check if the value is in one of those. And on the data profiling, it's a bit more complicated because there we don't know in the beginning like what exactly is in this particular column. We just know that it could be one of these columns that we want to map it to. So then we are kind of looking into like common values that we commonly see in our data and try to see if it is matching with those data, and then have like a suggestion that this is probably what the data column would be, but it is not able to give like 100% certainty. It still needs to be checked by the user if it is a correct match or not.
Question here on the execution engine. Like you moved from local to Kubernetes executions, right? Did you see any performance gain or changes on that?
On the Kubernetes executor on the Airflow?
Yeah.
So this is still a work in progress. We have not, I don't have answer to you yet, but it's pretty certain that the isolation will be helpful for us. Like even if the performance isn't really the biggest limitation for us. The problem is that when the scheduler pod dies, and especially if it's like one of these like stronger outages, that it's not able to self-heal and it prevents anything from happening. So that's kind of the main concern. But with this, it provides the isolation that now the scheduler is actually just now scheduling these tasks instead of having all this processing happen. So if any of those tasks fail, it's a problem for that particular DAG, but not for everything. And that's the part that we are really looking forward to having with this system.
Thank you for a great talk. Are there any tools that you use for data profiling? Any libraries that you could tell us more about?
Yeah, that's a good question. So in the data profiling, we actually, because the kind of how it started was that there was a developer integrating a new data source, and then like these data issues seemed coming up, and it was like, wow, man, like I wish I had something to deal with this. And then kind of started to, on an ad hoc basis, that yes, I will put on some Spark code to to look through these columns. And that's kind of how we started to build that we then started to generalize that and make it more to handle more edge cases and so on. So we started from scratch and built it in Spark. So it's like built in-house using Spark.
Yeah, thank you for the talk. And I want to follow up with that, the Airflow questions. So because this year, actually so last year, Google released an Airflow, a host Airflow like Composer. It's like one of the solutions that based out of the Airflow framework. And I think in that solution, they also do they also run Airflow on the Kubernetes. And I wanted to, from familiar with that solution, how you compare using Composer versus building your own in-house Kubernetes Airflow cluster.
Yeah, that's an interesting question, and I have not looked deeply enough to the Composer to really make any comparisons. So then maybe I will look into it in the future and see what I would think about it at that stage, but I haven't really looked into it deeply enough yet.
Hi, thank you. I'm wondering where in this process do you start strictly enforcing a schema, and how do you deal with changing the schema from the sources on the left?
Yes. So in when we are extracting the files, we obviously keep them, we actually keep them exactly as they are, if that is in any way possible. So, and after that, when we transfer them to Parquet, we keep the schema of the original format. And that can be whatever is provided to us. And those rarely have changes in them. And if they would, then we would need to consider that in the commonization step when we are putting this data into common schema. And then after that, we keep it strictly in that common schema. And for that, we have source of truth for what that schema is, what it should look like. And at times, if it really need be, we make changes to that and have like a second version of the common schema. And that's kind of a bigger project then, that if we change the common schema, we often need to reprocess the data that we have to backfill to meet the new schema requirements. So sometimes, we don't do that very often. We have had need to do that like once so far, and in that case, we then just reprocess the data that we had.
With the data validation tool, if you have just some small number of records that fail the validation, do you reject the whole data set and try to fix the errors and try again, or do you have some sort of error buffer or something?
That is actually an excellent question. The one that we are like discussing and dealing with on a daily basis. That we see something a little bit wrong, but like, what do we do now? Like, what's going on here? And it can be very tricky, actually, even to notice whether it is actually wrong or not. Because some of the data that we get, like there's so many different ways that you could present it, that first when you see something that it doesn't match the validation, we are like first we have to figure out like how did this happen? Like what's going on here? Is this truncated data that's why it looks so weird, or what's going on? And really those considerations will then decide what we actually do with it. And then if it is on a very, we usually at most, we would filter out some of the bad data if there is very little of it. If there is much more of it, then we kind of have to like really think about what we're gonna do with this. That are we going to kind of go back the chain to see where that problem is coming from, because we don't want to provide that bad data to the users of the data. But that is very much on a case-by-case basis.
Have you had issues where the structure of the data or the schema changes drastically because of some business need or business requirement? And how have you handled that?
Yeah, so there's kind of two sides to that. From the business perspective, it's mainly been like there was once where we really had to like change our schema. But we haven't had that many times because we started with very broad definition that we were, the data scientists, they always want everything. So then we had to really put pretty much everything that we could consider to be useful to have in the common schema. And then only afterwards, when we had like matured the products enough to see what actually is useful and what is not, and which data columns are not often filled in the data sources that we have, that then we decided that, okay, now let's narrow it down a little bit. So we don't have those changes too often. And then on some of the data sources that have like more rare refresh cadences, there we actually know that almost every year they are changing the schema. So we kind of have to be on alert that once we get access to that data, we want to get it processed as fast as possible, but we always have to check that the schema, what are the changes this year? What do we need to do now? And that's kind of a painful process, but it doesn't happen too often, so we just deal with it when it does.